Alright, so here we are in the last section of Chapter 3, and we'll be discussing some periodic trends in those periodic table properties. And we've already hinted a lot of these, especially when we were talking about electron configurations in the last chapter, which is really based on the orbital filling order. If you recall, we talked about group 1 metals, or group 1A metals if you prefer that nomenclature, as being very active. So we'll just continue to explore that idea and look at how reactivity and chemical properties vary across the periodic table. If you recall the last segment when we talked about abbreviated electron configurations, that was a convenient way, especially when we get to the heavier elements, of just instead of writing the 1s2, 2s2, 2p6, so on and so forth, we could just put the noble gas that precedes it in brackets there and finish off with what's in that current final period of the table. That's because it's the valence electrons that do the chemistry. They determine the chemical properties of the elements. They're the outermost highest energy level electrons, and they're related to the group number of that element. And that's why these are the electrons that we really care about. These are the ones that do the chemistry that we're going to be learning about throughout the semester. So in our example here, we have phosphorus with 5 valence electrons. Well, if you look, phosphorus is a group 5A element, or 15 if you prefer that nomenclature. But the reason for that, the reason for the group 5 properties, 5A specifically, is it's a 3s2, 3p3. It has 5 electrons in that highest principal energy level 3, and that's why we expect certain similar behavior between nitrogen and phosphorus and other members of group 5A or group 15 in the periodic table. So every element in the same group in the periodic table has the same number of valence electrons, with the exception of helium. How we have that placed in group 8A or group 18, it has just the 2 valence electrons because it has just the 1s orbital to fill in the ground state. All the other members of group 8A or group 18 have 8 electrons. And that's why we put hydrogen where we do, even though it's not a metal. We put it with the group 1A or group 1 metals because it has the 1 valence electron. So aside from that important exception of helium, which doesn't do any chemistry anyway, so we don't really care so much about helium for chemical reasons in the course, we look at every member of a group having the same number of valence electrons. It doesn't mean they have the same chemical behavior, but we expect similar trends. And so in our example here, we're looking at elements in group 2A or group 2. They all have 2 valence electrons. They've all just filled their s orbital for whichever highest energy level they're in. So beryllium is filled the 1s and the 2s orbitals, and magnesium now is just filled the 3s orbital. Calcium's finished filling the 4s, and strontium's finished filling the 5s. So these all have 2 valence electrons, and they all tend to be pretty reactive metals because they can lose those 2 valence electrons pretty easily. Beryllium, being the smallest member, tends to have the least reactivity in group 2A or group 2 because the electrons are really close to the nucleus. When you get down to something like strontium or barium, those 2 valence electrons in that 5s or 6s orbital are very far from the nucleus. They're very high in energy, and it's relatively easy to remove them. And so that's how we get the reactivity trend. As for metals, the more active the metal is, the one further down in the group. Okay, so if we look at this table 3.11, our electron dot symbols, notice those electron dots are trying to show the number of electrons in the valence of the elements. So we have the various members of group 1A or group 1. They all have 1 dot just to the right. In group 2, we have 2 dots, 1 up above and 1 to the right. And then group 3A or 13, we have the 3 dots. 4A or 14, we have the 4 dots. 5A, so on and so forth. So we have the same number of dots in the valence electron dot symbol as the group number if we're using the A nomenclature. Okay, so let's take a moment now to see how this is going so far. We've had just a few slides and just a few ideas so far, so hopefully it's going to be a pretty easy learning check. The learning check here is to identify the number of valence electrons for each of the following. So number 1 is oxygen, 2 is aluminum, and 3 is chlorine. And so we're looking just for the valence electrons for each of these elements. So make your selection, pause the video if you must, and when you start back up, we will see how you did. Okay, so looking at oxygen, oxygen's a group 6A or group 16 element, so we would expect B, 6 valence electrons to be present. So hopefully you answered that one correctly. Again, it has a total of 8 electrons, but those 1s electrons don't really have much to do with the chemistry. It's the valence electrons, those 6 in principal energy level 2, that are handling the chemistry. Number 2, aluminum, which is a group 13 or group 3A metal, should have B, also 3 electrons this time. And finally, chlorine, which is a group 7A or group 17 element, should have C, 7 valence electrons. So hopefully that went well. Let's have another learning check just to make sure and see how you're doing with these concepts. Okay, so again, we're looking to identify the number of valence electrons. This time we're going to look at calcium. Then we're going to look at anything in group 6A or group 16. And finally, we're going to look at tin. So for each of those elements, please, or groups in the case of number 2, please identify the number of valence electrons. Pause the video if you must. Otherwise, let's see how you did. Okay, so we had calcium actually as one of our examples when we talked about the group 2A or group 2 metals, and therefore hopefully it was pretty easy to identify choice B, 2 as the number of valence electrons for calcium. For number 2, anything in group 6A or group 16, in the previous learning check we had oxygen, which is a group 6A element, and we saw that it had 6 valence electrons, so this time 6 was choice C, and that holds for any member of group 6A or group 16 in terms of their valence electron count. And finally, tin, which is in group 4A or group 14, we would expect B, 4 valence electrons. Hopefully you're getting the hang of this. We've got one more learning check and then we'll move on. Okay, so now instead of using the periodic table, let's take a look at electron configurations. And for each of the following electron configurations, let's identify the number of valence electrons for the element with that electron configuration. So go ahead for 1, 2, and 3, make your identification. Pause the video if you must, start back up, and we'll see how you did. Okay, so when we're looking for valence electrons, we're looking for the highest value of n. So for number 1, that 1s2, 2s2, 2p6, that's all core electrons. It's the 3s2, 3p1 that identify the valence, and therefore there's a total of 3. There's 2 electrons in the 3s and then 1 electron in the 3p, so 3 valence electrons. For number 2, again, the 1s2, 2s2, 2p6 is all core, and so it's just the 3s2 for a total of 2 valence electrons. And now finally, number 3, 1s2 is our core, 2s2, 2p5 is a total of 7 valence electrons. So hopefully, whether I'm giving you the element symbol or a description of the group or the electron configuration, you're feeling comfortable identifying the number of valence electrons based on any of those features. If that's not the case, please try additional problems in the text, check out the homework set, and certainly get in touch with me if there's anything I can do to help you. Alright, so we already saw this in one of those tables earlier on in this subtopic, but electron-dot symbols. An electron-dot symbol will be useful to us because, first of all, it indicates the valence electrons as dots around the symbol of an element. And secondly, if we look at a specific case here for magnesium, we can show those 2 valence electrons as single dots on the sides of magnesium. And it's not so critical for the metals in terms of where we place these dots, but for the non-metals that tend to do a lot of covalent bonding, we're going to see that the electron-dot symbol helps us to get the bonding pattern for most of those non-metallic elements. So if we are following this convention, especially if it's not a convention that you've learned in the past, the way to draw the electron-dot symbols for the elements in groups 1A or 1 to 4A or 14, we use single dots that we just place. So for the members in the group 1A, sodium here in this example, we just put a dot to the right. Then when we move to group 2A, we put a dot opposite that dot over to the left. And then when we move to group 3A, we put a dot up above as well. And then finally, when we get to group 4A, we have the 4 dots arranged sort of like the 12, 3, 6, and 9 positions on a clock. Once we go beyond group 4A or 14 with the main group elements for groups 5A to 7A, or really even 8A, we would have pairs now. So it doesn't matter so much where you put the pairs. Most of the time, I've seen the pairs above the P here in the case of phosphorus or oxygen, but here they show the pairing first to the left and then to the right. That is not really critical. It's just a matter of having the correct number of electrons and remembering that once we get beyond 4 valence electrons, we're pairing those valence electrons. And that's going to help us understand the bonding scheme and the bonding pattern. The group 8A or group 18 elements, the noble gases, aside from helium, which has just the 2 valence electrons, all the rest have 8 valence electrons, and therefore they would have 4 pairs around them. So just like chlorine, but for say argon, there'd be an extra dot down below to give 4 pairs. So however you do it, whether you do them across from each other like our text does, or right next to each other first, the key idea is to make sure that all the members of a given group have the same number of valence electrons, the same number of dots here for these electron-dot symbols. So our example below is all the atoms of elements in group 2A have 2 valence electrons each. So we see the electron-dot symbol for beryllium and magnesium and calcium and strontium and barium. They are all following that same pattern. The only change is the particular element symbol, right? In all cases, you've got a dot to the right and a dot to the left, indicating those 2 valence electrons. Okay, so let's pause now for a learning check, see how we're doing with these electron-dot symbols. So in this learning check, we have 2 questions. Each of them is showing the electron dots around some unknown element x. And so for the first case, we have just a single dot above the x. Is that the electron-dot symbol for sodium A, potassium B, or aluminum C? And then the next example, we have a total of 5 electron dots. Is that the electron-dot symbol for A, boron, B, nitrogen, or C, phosphorus? So go ahead and make your selections, pause the video, and then when we start back up, we'll see how you did. Okay, so this was a bit of a tricky one, right? Hopefully you didn't fall for the temptation to just pick one element, because for number 1, that single dot could be sodium or potassium. They're both in group 1 or group 1A, and they would each have just a single valence electron. Likewise, for number 2, both nitrogen and phosphorus have 5 valence electrons. They're both group 5A or group 15 elements, and so that electron-dot symbol could equally represent either nitrogen or phosphorus in this case, either sodium or potassium in the first case. So just get used to that idea that anyone in the same group is going to have the same number of electron dots, with the exception of helium having just 2, everybody else in group 8A or group 18 having 8. Okay, so the first real trend we're going to follow here based on position in the periodic table is the size of the atoms. So atomic size is described using the atomic radius. And the radius, of course, is the distance from the nucleus to the outermost valence electrons. It increases going down a group because we're increasing the number of the principal energy level and therefore increasing the size of the orbital types that we're describing. It also decreases going across a period from left to right, and this may not be very logical to you. You might think that, well, the elements tend to get heavier as you move from left to right within a period. Shouldn't they be getting bigger? And no, that's not the case, because what's happening is we're taking from the left, the s orbital is being filled in that valence. As you move across to the right, you're starting to fill the p orbitals in the main group. And those s and p orbitals are roughly the same distance from the nucleus, so that additional electron isn't going out any further. It's really actually being pulled in tighter because the nucleus is also gaining a proton for every element position, we move from left to right. And so that nuclear charge increase is actually causing the electrons to get a little tighter in the electron cloud and cause a smaller atomic radius. And so here we see those trends on the periodic table. As we go down the periodic table, atomic radius increases. So for a given group, the largest member of the group is going to be toward the bottom of the table. That, I think, makes sense to everybody. It's very logical. The atomic radius decreasing across, as I mentioned on the previous slide, that seems to be counterintuitive. That's the one where people tend to struggle. And again, they do tend to get heavier. The elements tend to get heavier as you move from left to right, with just a couple important exceptions there. But that's the overall trend, is you're increasing the mass of the element, the atom, as you move from left to right in the periodic table. But again, the key feature, what changes the identity of the element, is the number of protons in the nucleus. So you're increasing the number of protons in the nucleus. That increases the nuclear charge, and that causes the electrons, the valence electrons, to be more strongly attracted to that higher nuclear charge. So if we're looking for the smallest element, we're looking up and to the right, so that would be helium. If we're looking for the largest element, we're looking down and to the left. So in this particular table, which doesn't include period 6, we have rubidium. If we had the full periodic table, obviously we'd look down and to the left, and it would be our period 7, 1A, or 1 element of francium. Alright, so let's pause now for a learning check, and we'll see how well you're understanding these atomic radius, atomic size trends. So for this learning check, for each of the element pairs, select the element with the larger atomic radius. So for number 1, would lithium or potassium have the larger atomic radius? For number 2, would potassium or bromine? And for number 3, would you expect the neutral atom of phosphorus or chlorine to have the larger atomic radius? So make your selection from each of those pairs and pause the video if you're still thinking. Start back up. We'll see how you did. Okay, so the first one was hopefully an easy one. Potassium's further down in the same group and therefore is the better selection. So potassium is larger than lithium. For number 2, potassium and bromine are in the same period of the table, but since potassium is further left, it would be the larger atom. And then finally, for the third option, we have phosphorus and chlorine, also both in the same period, relatively close together, but phosphorus is just a little bit to the left, and being to the left in the same period obviously means we would expect it to be the larger atom. So phosphorus is larger than chlorine. Hopefully you got those. If you're still struggling, my guess is it's probably 2 and 3 that caused you more trouble than number 1, and it's, again, just a matter of practice, getting used to that idea of electrons being pulled closer to the nucleus as you go across from left to right in the periods. Alright, our next trend is actually very much related to atomic radius if you think about it, and this is called ionization energy. Ionization energy, as we see here, it's the energy it takes to remove a valence electron from an atom in the gaseous state. So we take a gaseous sodium atom, we add energy to ionize it, and we get now the gaseous sodium ion plus that electron that we removed. This decreases down a group and increases across a period from left to right. And that's the same sort of idea as the atomic radius. If an electron is further from the nucleus, it should be easier to remove. So in the case of the largest atoms tend to be down and to the left. So it should have relatively less energy as you move down a group and relatively more energy as you move left to right. If the leftmost are the ones with the largest radius and therefore the electrons least attracted to their nucleus, it should not take as much energy to remove an electron from that type of element compared with an element to the extreme right of the periodic table, like the noble gases that are very happy with their electron configuration, and it's much more difficult to remove an electron in that case. So down, as you move down the table, periodic property of ionization energy decreases. As you move from left to right, ionization energy increases. And here we see that graphically, and you'll notice there's a couple of key blips there. It's not a nice smooth trend line. Aside from hydrogen to helium, that behaves itself, right? Hydrogen is easier to remove the electron. It just has the one, and it's further from the nucleus. Helium, it has two. They're closer to the nucleus, so to remove one requires more energy. Once we get into the multi-electron systems there, you'll notice that it takes relatively little energy to remove from group 1A. Then group 2A is a little more, and then for seemingly unknown reasons, it suddenly drops again for group 3A. And that's because when we have a filled orbital like the 1s or 2s or 3s, we have a little bit of extra stability. So it's actually preferred state for the group 2 elements compared with the group 3A elements to have that electron removed. So having a filled s sublevel gives us a little bit extra stability. Then when you get just a single p electron, it's slightly easier to remove that one. We also see when we have filled a p sublevel, so the nitrogen, phosphorus, arsenic, the group 5A or group 15 elements, because they have one electron spin up, spin up, spin up in each of the three p orbitals, they get a little extra stability. It's a little harder to remove them than to remove the electron from, say, oxygen or sulfur, selenium, any of the group 16 or group 6A elements. And then the trend continues, and it gets much harder to remove as we get to the noble gases. They're very happy with their electron configuration. Those electrons are very difficult to remove and require the most energy in a given period. I don't tend to ask about the exceptions, like the comparing beryllium and boron, for instance, or nitrogen and oxygen. I tend to be interested in the overall trend, but it's important that you do realize that there are some exceptions, and that exceptional behavior tends to happen when you've either filled an orbital, like the s orbital here, or half filled an orbital type, like the p orbitals. And if we're looking at some properties here of the elements based on their type, ionization energies of metals tend to be low because the metals tend to be to the left of the table. The ionization energies of the nonmetals tend to be high because the nonmetals tend to happen over to the right of the table. If we wanted to compare within the metals, for instance, like we see here in this trend, lithium, sodium, potassium, it tends to get easier to remove as we go down. For the nonmetals, it tends to also get easier as we go down. So if you're looking for the highest ionization of all elements, you're going to be looking up and to the right. And if you remember that last graphic from the previous slide, helium is going to be the toughest to remove the electrons from. It has a filled s sublevel. It's nice and stable. Those electrons are really close being in the 1s orbital. It's very difficult to remove them. If you want to think about the easiest metal, or the easiest element to remove, you're looking in the metals and you're looking down and to the left, and you're right back to francium, just like we talked about when we were thinking about what would be the largest element by atomic radius. Okay, so we just stopped thinking about francium as being the largest by atomic radius, the lowest ionization energy. It's also a good example of metallic character. Metallic character increases when an element can lose its valence electrons more easily. So it tends to increase as you go down a group, and it tends to increase as you go left, or decrease as you go from left to right. So if we're looking for the highest metallic character, the most metallic element on the periodic table, we'd look right back to francium. It's the largest, it has the lowest ionization energy, it has the greatest metallic character. We're looking for the least metallic character, we're going to look up and to the right, and we're right back at helium, which we said also has the highest ionization energy and the smallest atomic radius. So if you can keep these things in mind, have these key elements, or at least the key features of where you are in the table, then you'll be doing very well with keeping these key trends straight, because they're not always the same, especially when we talk about the decrease in ionization energy as you go down, whereas you increase in atomic radius, for instance. And here we have at least the main group elements and the key trends with metallic character. So as we move down the periodic table, we increase in metallic character, and based on what they show here, you can even see that in group 3A or 13, boron is a metalloid, whereas aluminum, gallium, indium, thallium, those are all metals. In group 4A, we've got carbon as a nonmetal, silicon and germanium as metalloids or semimetals, and then finally tin and lead as true metals. So as we move down a group, at least for groups 13, 14, 15, or 3A, 4A, 5A, we see that we go from being either a metalloid in the case of group 3A or a non-metal in the case of group 4A and 5A to moving through those metalloids and finally to true metals based on moving down and therefore increasing metallic character. Likewise, we notice that as we move to the right, we tend to go from metals like lithium and beryllium in the second period through metalloids like boron into the true nonmetals, carbon, nitrogen, oxygen, fluorine, neon. So obviously we have gone from metals to nonmetals, which means as we move from left to right, we have decreased metallic character. Okay, and finally here, table 3.12 gives a nice summary of these trends. So we have periodic property, and then what happens as you go top to bottom of a single group, a vertical column, and then finally left to right across a period, a horizontal row. So for the valence electron count, it remains the same as you go from top to bottom of a group. Again, we talked about group 18 or 8A and helium being the one exception, having just the 2 valence electrons, whereas everybody else there has 8. As we go from left to right across a period, the number of valence electrons increase. Group 1 or 1A has 1 valence electron, 2 or 2A has 2, and we just increase one by one all the way up to group 8A or group 18 having 8 valence electrons. Atomic radius, as we go from top to bottom of a group, that will increase due to the increase in the number of energy levels, and as we go from left to right, it decreases because of those increased number of protons having a stronger attraction for the electrons. The valence electrons in particular are pulled closer, all the electrons, but the valence electrons that we're following are pulled closer to the nucleus, so the atomic radius actually decreases from left to right as we're increasing the electron count, but also increasing the proton count in those elements. Ionization energy decreases as we move from top down for the same reason that atomic radius did. We're having electrons in higher energy levels, and those electrons are further from the nucleus, therefore we don't have to put as much energy in to ionize those elements. As we move from left to right, it increases because, as we said in atomic radius, the nuclear charge is increasing, and it's causing the electrons to be held more tightly by the nucleus. Therefore, it takes more energy to remove those electrons from that are experiencing that higher nuclear charge. Finally, for metallic character, as we go from top down, it increases again, just like atomic radius, because the electrons are more easily removed. And then finally, as we go from left to right, metallic character decreases. We move from the metals on the left-hand side of the periodic table through to the nonmetals on the right-hand side because those electrons are more tightly held and less likely to be lost. And therefore, since metals tend to be elements that readily lose electrons, elements that want to hold their electrons tightly are very low in metallic character. Okay, so hopefully that summary of the periodic trends in the previous slide helped to tie all this together for you. Let's confirm that with a learning check. And in this learning check, you're going to select the element in each pair with the higher ionization energy. So number 1, is it lithium or potassium? Number 2, is it potassium or bromine? And number 3, is it phosphorus or chlorine? Go ahead, pause the video, start back up when you're ready to see how you did on this learning check. Okay, and there we have it. Lithium has a higher ionization energy than potassium. So if you think back, we used these same examples with atomic radius, and there potassium was the right answer. Now lithium is the one with the higher ionization energy because it's smaller, its electrons are more tightly held by the nucleus, and therefore it takes greater energy to remove a valence electron. For number 2, bromine is going to have a higher ionization energy than potassium because bromine is further to the right, and we know that as we move from left to right, those elements within a period are going to have a decrease in radius and an increase in ionization energy because the electrons, the valence electrons specifically, are being more tightly held by the nucleus. Finally, chlorine is going to be higher in ionization energy than phosphorus for the same reason as number 2. It's because chlorine is further to the right. It has a couple extra electrons, but it has also a couple extra protons in its nucleus compared to phosphorus, and it's that nuclear charge and the ability of the nucleus to more tightly hold those electrons, which means you're going to have a higher ionization energy. It's going to cost more energy to remove electrons from chlorine, which holds them more tightly than it would from phosphorus. If you're struggling with these, in particular, the fact that a couple go hand in hand, ionization energy sort of bucks the trend of atomic radius and metallic character. So practice those a little more. Let me know how I can help. Otherwise, we've finished chapter 3 now and are ready to move on to chapter 4.